trying to fly like a bird, we wanted to understand a particular maneuver, which is landing on a perch. And before we had the birds working, we asked the question, could we even do this with a fixed wing aircraft? Okay? The reason it's hard, you can sort of summarize in a single slide. So aerodynamics 101, if I have an airfoil and low angle of attack, no problem. The airflow stays attached to my wings. I get nice, simple aerodynamic effects. If I go to a small angle of attack, the airflow can stay attached to the wings. Still, in these models, sort of linear or piecewise linear models of the lift and drag coefficients work very well, and I have very good control solutions that can work for modern aircraft in these regimes. If you go up and install your wings, then you get into a much different flight regime. Suddenly you've got a very complicated flow on the back of your wings, unsteady, high varying, much more difficult to model with the lump parameter, a differential equation model. And as a consequence, we don't see many modern aircraft flying in this regime. So even at some of the best aircraft we've ever designed, for like these carrier landings with the fighter jets, carriers landings are done at very low angle of attack to be conservative. They have a guide wire that catches a hook on the back of the plane, and in fact they have to come in at a low angle of attack at high speeds, because if they fail to grab the hook, then they have to hit the thruster to not plunk into the ocean on the other side, right? And birds just don't do that at all. Birds are always landing on a perch at extremely high angle of attack. You just make out the smoke trails behind you, but this guy's actually coming down. He's probably at about 90 degrees angle of attack instantaneously. They're in a very different flight regime. So you might ask, what are they doing? Are they just sort of taunting us with their post-stall aerodynamics, or are they actually getting a big dynamic advantage, right? So it turns out you can do some quick dimensional analysis, and they get a lot more drag, basically, than the aircraft, and they get to stop a lot faster by going into this regime. And it's simple to understand. So first of all, if you expose more surface area to the oncoming flow, then you get more viscous drag, of course. But the dramatic thing that happens is when you get separation on the back of the wing, what effectively happens is, if you think about it, the air can't bend around the wing fast enough, you're left with a low pressure area behind the wing. You've got a pressure drag that comes in. It adds a significant amount of drag. These birds are basically hitting the air brakes and can come to a stop in dramatic fashion. And despite basically having this parachute out, exposing them to an enormous amount of drag, they're still doing exquisite landings, like hitting a branch on a tree. We can only hit a carrier, right? So we wanted to see if we could try to make a plane do that. Tried to build the simplest possible plane that could reproduce that sort of a result. It's a glider. There's no propeller. It's got flat plate wings. The wings are bent up with some dihedral, so that it has passive stability in roll. It basically has no interesting dynamics out of plane. It's only interesting in the longitudinal plane. It's just got one actuator, which is the elevator, remotely controlled, off-board sensing and control. It's in a motion capture environment.